going to present this pillar on intuitive robot programming, which contains technical challenges 5 to 8. So why are we having challenges on intuitive robot programming? Well, because to work with robots, they have to be programmed. They must be programmed by somebody. And programming the traditional way, programming by coding, by writing code, is not an easy thing. It's hard for those who are not programmers, and because robots are intended to be used by workers in industrial production, they can't be expected to be also proficient programmers. So we want to give them solutions, alternative solutions that are based on extended reality technologies that can help with all of this. So specifically, we want interactive technologies, interactive techniques based on XR that can be used to teach robots new skills rather than program them. So that mindset change is something that we want to facilitate. So the worker is teaching the robot, is transferring some skills, and the code will be generated automatically behind the scenes. So the person programming or teaching the robot doesn't need to be thinking about the code, which will just happen. So there are 4 challenges again here. We've seen this list earlier, and I'm going to go through them one by one. So not to delay any further, I'll just move on to the first one, which is the challenge of XR-based system to program on-demand tasks to stationary robots. So we focus here on stationary robots in industry, which would be something like robotic arms that are used for production. And the background here is that in industrial production, nowadays it's very important to be flexible and to make changes in production very frequently to adapt to requirements from the market, and customization is something that needs to be offered. So great robots allow doing this. Robots, once they are programmed, they allow you to change production. But as we said, we want workers to be able to do that programming or that teaching in an easy way. So for this challenge, we want applicants to develop XR-based programming tools for stationary robots. So tools to program fixed stationary robots like robotic arms, with the core functionality of being able to program those intuitively, as if they were teaching the robot rather than, as we said, there will be no coding. So somehow transferring knowledge to a robot as if it was a colleague of yours next to you at the workplace. And we expect that there will be some good support for swift reconfiguration of the production. So no hassle, easy change from one production to another as far as that's possible. Which scope of tasks should be considered? Well, it could be applicants could focus on simple actions, simple frequent actions in production, or they could also look at linked series of actions that turn into a more complex sequences that are useful for some processes. So that's still, again, in this requirement is fairly flexible, what is being asked here. There are certain key features that are expected in this challenge, and pretty much also in the other 3 ones that will follow later. One is that it should be user-friendly, as we've mentioned for other challenges earlier too. Flexible, meaning that it should not be developed for a very specific, rigid application, but should be used in a scope of situations, scope of scenarios, and it should be precise. So if you're going to be programming a robot, precision is going to be as good as it's required for the application. Something that we expect is that programs generated through interactions, because we're talking about programming robots through interaction in extended reality. So the programs generated in extended reality behind the scenes should be executable in real robots. So it shouldn't be just like some sort of animation that only works in XR. It should be something that can be transferred to reality. So architecture should be kept taken in mind. And the intended users here are, well, creators of XR contents who are thinking about creating contents for students, trainees, production workers. So that's the first challenge in this pillar. The second challenge, we're talking about programming mobile robots instead of stationary ones. And we're thinking about mobile robots in intralogistics operations. So the background here is that mobile robots are essential in intralogistics operations, and for tasks like material transport, inventory management, navigation through complex environments. So there's a number of tasks, and there will be others that are typical in intralogistics scenarios. So here we're expecting, as the central challenge, to develop an immersive virtual learning environment, maybe a simulated warehouse or factory, for teaching mobile robots programming and management. So it's not just programming a robot to go from one place to another, but also to have some control over what's happening as they are executing the task. So programming and management. Core functionality here is, well, I mean, the scope of tasks here, I've already mentioned them in the title, which would be, these are, again, just some examples, but material transport, inventory management, complex navigation through, fairly complex environments, but there can be others as well that will be accepted for the challenge. And the key features here are the same ones as earlier: user-friendly, flexible, precise, in the context that now affects to intralogistics, like navigation, for example, and, well, executable in real mobile robots in this case. The solution will be delivered as a library of XR tools to simulate those environments, and to where they can be programmed and managed. So we support with all of that. And users will be very similar as earlier, creators of XR contents for students, trainees, and operators in intralogistics activities. Moving on to the next one, the third challenge in this pillar takes into account programming robots for assembly and packaging tasks. So focuses specifically on that very important family of tasks. And here, some aspects come into focus, which are basically efficiency and high quality of the assembly and the packaging that are carried out. So quality is always important, but here maybe so much more. The challenge, so, is to develop an immersive virtual environment, learning environment, maybe a simulated industrial facility, for teaching robot programming for assembly and packaging tasks. And some core functionalities for the assembly aspect would be that there's support for programming tedious, repetitive tasks, which are very common in assembling, and where precision is needed, and where dexterity is also important. So the combination of skills and capacities and capabilities between robot and collaborating human, supporting those and being able to share between machine and human, that will be important. For packaging, functionalities that are important. Again, I was mentioning already quality here, and we've identified that important tasks here for packaging can be wrapping, sealing, labeling, preparing goods for distribution. Yeah, and we've added as a key feature that these tools should raise awareness on quality issues, on the importance of doing things with high quality, with precision and correctness, regarding, for example, the orientation and placement of components in materials, and we may think about like labeling it correctly and so on. The solution delivery, again, same as earlier, would be a library of XR tools to simulate an environment where these activities are being programmed and are being carried out. And users, well, very similarly as before, will be in this case for workers that will be carrying out this type of tasks. But basically, this is intended again to creators of XR contents with students, trainees, and workers in mind. And then finally, we've added more open challenge, where programming would be for scenarios or tasks of manufacturing that are not clearly specified, and therefore applicants are free to propose their own ones. So applicants are free to propose XR tools for learning robots learning robot programming applications in various manufacturing operations. And some examples of those, so this is a bit of a brainstorming, would be, for instance, machine tending, machining, inspection, repairing, but there will be many others as well. They should be real-world scenarios that can illustrate real challenges that workers may find, and robots should be programmed to solve. In solving problems, that it would be good to have, we expect to have a focus on problem-solving strategies. So tools should illustrate approaches to optimize the processes that are being programmed, and to improve manufacturing quality, and to support human-robot collaboration, to optimize the sharing between tasks, or sharing of tasks between human and robot. Key features would be the same as earlier. The solutions developed would also be a library of XR tools with the focus on the selected production tasks for the applicants in this case, and same considerations for the users. Nothing changes here, but specific for the application area in industrial production selected by the applicants. And I'm going to continue like earlier with an example of a development that we've conducted in the project. So this video shows how a person, a user, a worker in a virtual environment shared with a space shared with a robotic arm, the person is going to be indicating destination points for the robot to go to, and the robot, through an architecture that is ROS-based, and therefore is the same architecture that the real version of this KUKA robot would find in the real factory, is going to calculate trajectories, is going to let the worker or the user know if that destination is reachable, will show a preview, and then the person will decide if it's worth, if it looks good, then it will order it will command the robot to execute the trajectory. And I will do this 3 times. The first and the third one will be successful, and the second one will not be successful because the requested destination point is not reachable. Let's watch the video.
I'm sorry, Johan, but we cannot hear the sound. Probably you need to share with the sound turned on the screen.
Right. Not totally sure how to do that on the fly.
Probably you can just stop the sharing, or you can describe by words, or you can stop sharing, and when you select to reshare, there's an option to share your sound as well. The system sound.
Yeah. Shall I do that? I'm going to give it really quickly.
Thank you.
Right. Okay. So I think I should be sharing already. And if I go back to the beginning of the video, let's see if there's not a lot happening until the user starts talking. But let's see if you can. Yeah, seems to be working.
Yes, yes.
Sorry about that.
Plan a trajectory.
So in low voice.
A valid plan has been successfully calculated.
I would like to execute that plan.
Executing the plan. The plan has been successfully executed.
Plan the movement.
Having some
Planning a path.
Yeah.
No plans have been found for this target pose.
Plan a path.
Planning a path. A valid plan has been successfully calculated.
Execute the plan.
Executing the plan. The plan has been successfully executed.
Right. So regarding the architecture around the virtual robot, that's exactly the same one that would have the robot, the physical, the digital twin would have found in reality. So everything that has been calculated here would have been executable in reality as well. So that's actually the end of my talk. Thank you very much, and sorry for the glitches, but we made it all the way to the end.